Okay, welcome to Physics 2820 Lecture 7. Today we want to talk about simple harmonic motion. So up to now we've been talking about projectile motion, falling particles, things that go from one point to another. Now we want to talk about kinds of systems that have repeating motion. Anything with repeating motion is said to be a periodic physical system. If an object is undergoing periodic motion and they're going between two limits over the same path, we sometimes call that motion oscillatory. And so oscillatory systems are everywhere in physics. You might be familiar with ones like guitar strings being plucked or any sort of vibrating things, a pendulum swinging back and forth, either inside of a clock or from a long rope with a mass. But they occur at lots of scales in physics, including the oscillations of atoms inside crystals. So there's lots of systems that undergo oscillatory motion in physics. Sort of the canonical one to explore is what's called a spring mass system. The idea here being you've got some mass M, and as you pull it towards the right, there's a restoring force that pulls back towards the left. If you push the mass towards the left, there's a restoring force towards the right. We call this combination of forces sometimes given the name of Hooke's law. Hooke's law is saying that the force exerted on a mass due to a spring is dependent on how far away from equilibrium it is. And there's a certain constant of proportionality, and we call that a spring constant. So whether or not you want to think just graphically about springs and masses like we did in Physics 1050, being pulled away from equilibrium or pushed towards equilibrium, in either case, it's all summarized in this equation right here, representing a spring force law, and so we've got the name Hooke's law. Again, X represents the position, minus X means that the force is always opposing the motion. Now, if you bring that in and add in Newton's second law, we're able to come up with an equation of motion for a mass spring system. So specifically, acceleration, the second derivative of X with respect to t, is dependent upon the net force or force per unit mass. And one of the things we talked about when doing oscillatory motion, whether or not this be in Physics 1050 or the beginning of Physics 1051, is that acceleration is a constant in the problem, or rather this coefficient right here is a constant in the problem, and we give it the name of the angular frequency or the natural frequency of the system. Basically represented as this number which is in front of the X. It means the acceleration is proportional to the negative of the displacement. Whenever you have that combination, that the acceleration is proportional to the negative of the displacement, we call that simple harmonic motion. That's the kind of dynamical behavior going on. And the coefficient K over M tells you how fast the system is oscillating. Okay. We know something about these solutions. We know that a simple harmonic motion can be modeled in terms of sine and cosine functions. We explored this in other courses in physics where we'll model the displacement as a cosine function, something that's going to oscillate up and down at a frequency of omega naught. There's optionally an amplitude which sticks in front of the cosine. And of course, you may recall that the second undetermined constant is the phase offset. How much, to figure out at what time zero is the system at equilibrium. And this is the kind of stuff we do in a mathematics-based course on physics or in first-year physics. Cosine, of course, is a periodic function. What that means is every period 2 pi, x of t repeats. The period at which it repeats, period, we give letter t, is the smallest time for which the function becomes itself again. That is, if you stick in t or t plus capital T, you get back the same answer. That's what we call a period. And it's related to the frequency right up here. If we know the frequency is the square root of k over m, then the period can be written as 2 pi divided by the square root of k over m. Of course, everything to do with cosines and sines are in radians, which is why the 2 pi appears. Sometimes you'll talk about frequency, not angular frequency, but normal frequency. The reciprocal of the period, square root of k over m over 2 pi. An important observation about simple harmonic motion is the period or the frequency, which are the same thing, They don't depend upon the amplitude, and they don't depend upon the phase offset. They only depend upon these constants in the problem, the spring constant and the mass. Okay, so that's what we remember doing from something in first year physics. And if we were to go along and think about the analytical solution, right? So the idea here is for a typical problem, so a particular derivative, something that looks like this. Okay. So there is a differential equation. It has the standard solution of a cosine or a sine. And let's just say, for the sake of argument, we take the simplest possibility. That would just be a situation where k is equal to 1 and m is equal to 1. So the angular frequency is just 1. And of course, if you start it off, so the function at the initial time has some initial displacement, and at the initial time, it has no velocity, then you're going to get curves that look like this, sines and cosines going back and forth. And we know how to solve that problem analytically. What we want to do is we want to solve this problem numerically. So let's look at the numerical solution. As we've been doing for the last 6 lectures, our tool up to this point has been Euler's method. That method allows us to rewrite any differential equation as a system of first-order DEs, and then approximate the derivatives using what's called a finite difference. The idea being, inside the problem, you have a derivative of velocity is equal to acceleration, a derivative of position is equal to velocity. Rewrite the derivative dx dt as the quotient, the change in x of t plus delta t minus x of t divided by delta t. That is the velocity. It's an approximation because delta t is not infinitesimally small, it's just sort of small. And this routine is what we've been calling Euler's method. So let's code it up and solve it for an oscillator undergoing simple harmonic motion. As before, let's just work on the simplest case. K is equal to 1, m is equal to 1. Here is a very basic code that solves this kind of problem. It's the same pattern we've been seeing. To solve these problems, we need some sort of code that's going to step through time. I've been calling these codes steppers. This code depends upon some initial conditions. x0 is equal to 1, well, v0 is equal to 0, an optional time step, and how long to run the model for. We start always by initializing the model. The variables in the model are time, position, and velocity. And what we want to do is we want to run this model so that at every time step, we can look at the state of the model. And as long as the program isn't over, we can calculate the acceleration. This is, of course, is the force. Acceleration is force divided by mass minus kx divided by m. And then we can use the Euler method to figure out what it's going to be. And what we've been seeing is it's x is equal to x plus v times delta t, and v is equal to v plus a times delta t. The way of writing this down is you're updating the position. You're going from an old value of x to a new value of x, from an old value of v to a new value of v. That is Euler's method. We typically want some code to be able to plot it. So here is a fairly simple code. I'm going to plot the data versus x, or the x variable versus t, the velocity versus t, and I'm also going to plot the analytical solution. That is, I know it's going to be a cosine and a minus sine. I'll talk about this third part of the block of the equation in a moment, and we'll put it all together in some application, something that sets up the model, steps through it, and then actually plots it. So if we run this code, what we're going to get is an oscillator, okay? So this is the idea. I can think about this code as x is varying between some maximum point and some minimum, and some maximum and the minimum. Velocity starts off at 0, but because there's a net force acting towards the left, it accelerates towards the left. It reaches its maximum speed when it's at equilibrium, when x is equal to 0, and it comes back up. Now I've plotted both the numerical answer and the analytical answer in orange. You can see that there is some error. One of the things we've learned, of course, is you can reduce the error by making the time steps smaller. One other thing we can do in an oscillator is we can also look at the energy associated with an oscillator. So the energy associated with an oscillator is made up of two components. One is the kinetic energy, and the other is the potential energy. At any moment in time, the total energy is equal to kinetic plus potential. And one of the results we learned in first year physics is that number should remain a constant proportional to the square of the amplitude. So what I want you to do now is just take this code. I have added in the code to calculate the kinetic, potential, and total energies. And let's see what the potential, kinetic, and total energy looks like for this graph. So I'll do it with you. As you see, all that I did is wrote some code to calculate the kinetic energy, the potential energy, the total energy, and then plot all of those on the same graph. And let's rerun that program. Okay, here we go. So this is the potential and kinetic energy. Potential is in orange, blue is the kinetic. And over time in this oscillator, there's an exchange. It's going from kinetic to potential, potential to kinetic, and back and forth. The green arrow is what the numerical method is showing about the amount of energy in the system. If you start off with k is equal to 1, a is equal to 1, the total of the amount of energy in the system should remain equal to a half at all time. It starts off at a half, but you can see that our numerical method actually is showing that the energy in this oscillator is growing in time. As you keep on going, there's more and more energy in the system. Clearly, something is going wrong. Energy must be conserved physically, but this numerical model is predicting that the energy should be increasing. Okay. Over time, this mass is going to start oscillating more and more. So what I'm going to do is take that same model that I just showed you, and I'll remind you or point out that this thing takes some arguments. Specifically, it takes a maximum time. If I take that maximum time, I can make it an interactive application, quite simply by saying interactive, the name of the application, and then saying this parameter will go from 2 up to 40, skipping by 2. dt fixed just means I'm going the time step to stay fixed at 0.1 and not make it interactive. So hopefully what you can see is this is the initial thing. As we run this for longer and longer codes, can you see that as the system is oscillating, orange again is the analytical solution, it's oscillating with the right frequency, but it's going wilder and wilder. It's moving faster and faster. It's moving further and further from equilibrium. The energy is growing quadratically as it goes along. It's going faster and faster and faster. We have invented something that is creating energy as this model moves around. Notice the energy started off at a half, and after 40 seconds, it's sort of more like 30 joules instead of a half of a joule. Okay. There is something wrong. The mistake is not in the physics. The physics is totally fine. An oscillator conserves energy. The problem is with the numerical method. What we've discussed so far is Euler's method is based on a finite difference, which is an approximation to a real derivative. Okay, so the idea is we're going to rewrite our derivatives as the change in x divided by the change in t. Or we're going to rewrite the derivative of v as the change in v divided by the change in t. Every time step, Euler's method introduces a small error. And for good or for bad, what the numerical method does is cause that error to grow in time. Now, this error depends upon the size of the time step. So I'm going to use an interactive again, but this time what I want you to notice is what the variable I am changing is the time step. It's defaulting to 0.1. It can get as small as 0.02, as large as 0.2, and the step size is 0.02. And this time, I'm going to keep Tmax fixed at a value of 10. And so if I use this app, what I can do is make my time step smaller. And I want you to see that as I make the time step smaller, the error is going down. Do you see the blue line and the orange line are looking closer together? The energy is staying closer to 0.5. So we can improve Euler's method by taking smaller time steps. Taking bigger time steps causes the problem to just get worse that much faster, right? So if you take big time steps, the energy is going to grow that much faster. The rate at which the energy grows is dependent upon this time step. Okay, now, although this appears to be a solution, just make your time steps small, there are some major problems with this. Okay. The problems with it are, number one, if you make your time steps smaller, you have to run the program for longer. We have to take physically more steps in time to get the same solution. Your program starts to run longer and longer. Maybe you've noticed this as you've done some of the labs or the assignments, that if you want to take not 100 steps, but 1,000,000 steps, it takes some time for the computer to actually calculate that. Even worse is every time you do the calculation, every time you run this program, what you're doing is you are adding small numbers, right? Back to the code. Here's the Euler method right here. You are adding these numbers. If delta t is very, very tiny, then you're adding a small number. One of the things we've learned is everything in a computer has finite precision. We're using what's called a floating point number system. Arithmetic has small round-off errors because you can't resolve every number with infinite precision. As you go through this loop and you do a lot of adding, it's incrementing a small round-off, otherwise known as a truncation error, every time. Over time, those successive additions start producing a lot of errors themselves, independent of the numerical error. So there's a round-off truncation error building up. Secondly, or thirdly rather, Euler's method itself actually turns out to be unstable for many problems, which means even worse than just the error growing, because of the nature of the physics, the errors can grow even faster than quadratically. They can grow exponentially because of an instability in the problem. Why the method is not working is the method is assuming that the velocity and acceleration are approximately constant during one time step. And of course, what happens is the velocity and the acceleration are always changing in an oscillator. And this is why the Euler's method fails to work. Okay, we can make an improvement. We can change our model just a little bit and get a really different behavior in the numerics. This is the Euler model. Euler model says to figure out the position at the next time step, you'll use the position at the current time step and multiply by the velocity times delta t. To figure out the new velocity, you take the old velocity and multiply by the acceleration at the current time step. What we're going to do is make one small change. We're going to use the velocity at the end of the first interval to calculate the position. Not the velocity. The velocity line is going to stay exactly the same. We're going to figure out the velocity at the end of the time step. We'll equal the velocity at the beginning of the time step plus the acceleration. But what we'll do is we will first calculate this line and use that new velocity to update the position. So the only difference here is which velocity we're using to update x. So here we go. Here's some code that implements an Euler-Kromer algorithm, which is what this is called. The code is exactly the same, other than, of course, I've changed Euler to Euler-Kromer everywhere in the comments and in the code. And there is a small change in the code up here where I've flipped the order from Euler methods to an Euler-Kromer method. Other than that, the code remains the same. All I'm doing is running this code and flipping over these two lines so that instead of first calculating x with the old value of v, we first update v, come up with the new value of velocity, and use that new velocity to update x. Take a look at the behavior of this new numerical method. Okay, first of all, this is with exactly the same parameters, a delta t of 0.1 and a t max of 10. Notice now that the energy stays around 0.5. Even if you were to run this model for a lot longer time, the energy is no longer growing quadratically with time. It's not blowing up over time. The energy remains bounded. Now, it's not perfect. The energy is wobbling around a half. It's not exactly a half. But what you can see the method is doing is it's adding a bit of energy and taking away a bit of energy every time step, so that on average, over a period, the angles, the number is right. In terms of these graphs, they look very good. If I increase my time step, I still will get some error, though that error always averages out. And the amount of oscillation in the total energy is dependent upon that time step. Obviously, if I make the time step much smaller, I get a much flatter response. That is, the energy in the system remains a lot closer to being equal. For oscillatory systems, Euler-Kromer is useful. Euler is not useful. Euler blows up for oscillatory systems. Euler-Kromer, and again, the only change here is instead of updating the position to a new position, what we do is we update the position, the velocity first, and use that new value to update v. Those changes introduces a new algorithm that is stable for oscillations. Now, one of the things you might be thinking about is saying, okay, well, if I got this idea of different points, maybe there are other algorithms I could play with. And I'm going to talk about one of these algorithms. I'm going to talk about something called the Euler-Richardson algorithm in a moment. But I really want to make sure that we are crystal clear on what this numerical methods are doing. I've tried to sketch this out before, but I'm going to do it one more time. Let me flip over here to some drawings. Okay, so hopefully you can see I have given you a sketch, and we're going to do, you know, like pan drawings. Let me see if this is going to work. What I want to do for you is sketch out the Euler method so it's really clear what variables are what. Again, here's the algorithm. The new value position is equal to the old value position, and we evaluate this thing at the current speed and the current acceleration. We're assuming we're going to start this model at some initial position and some initial velocity. Okay? Those are the initial conditions. Those are given to us. The way that these numerical models work is we're imagining we're going to figure out what their value is at different points in time, and we're going to do that for velocity and position together in sequence. The acceleration in a spring mass system is dependent upon the position. As far as the spring is pulled forward or back, that tells you what the acceleration is. So, because the position starts off at being very, very large, the force, of course, is very, very negative. The acceleration is very, very negative. What that will mean is the acceleration is going to start by being negative, and this velocity here is going to be incremented down to here. This is the new velocity. Its acceleration is based on the position initially. Positive position, negative acceleration in an oscillator. The change in position as you go from position 0 to position 1 is based on the velocity at that time step. Well, at that time step, the velocity is 0. So there is no change in the value of x1. That completes the first time step. The second time step says to figure out the position from here to the next one, what I do is I use this velocity. This velocity is negative, so I have to have a negative slope right here. This slope is v1, and that gives me the new point, x2. Notice that to figure out the slope of the velocity, what I need to do is calculate the acceleration. The acceleration depends upon the position. The position is the same, so the acceleration is the same, so the slope of this line is the same. So the velocity at the end of step 2 is exactly the same, but it's based on the acceleration at step 1. Next step. I need to figure out how to go from here to the next step. What I do is I look at my velocity at the current step. It's even more negative than it was before. So rather than a line being like this, I've got to draw a line which is much steeper. okay? It's much steeper because the slope is the speed or the velocity at that point. I use the acceleration right here. It's still negative, but it's not as negative. It's not as negative. There's less displacement. There's less acceleration. So what happens is I still go down, but I don't go down as far. This is V3. Its slope is based on the acceleration at x2. Okay, one more time here. At this point, the acceleration is very, very negative. So I take this thing, it's very, very negative. I slope all the way down. Whoa, this is really gonna, my graph isn't gonna work out, but it's gonna be fine. So there we go. That's gonna be, if this is x3, this is gonna be x4. But it's based on, okay, so that's what that one's gonna be. To figure out where the next point is on here, I am using the value of the acceleration based on this point. And now that acceleration is gonna be a positive number because the position is negative. And what that means is I'm now gonna be sloping up. Why am I sloping up? Because the acceleration is based on x3. Okay, so here goes the basic dynamics. This is how the Euler algorithm is eventually going to do this and simulate the solution. In contrast, Euler-Cromer. We can go through this a little bit faster now. We start off at the same initial point, x0. We start off at the same initial velocity, v0. Those have not changed. The difference in the algorithm is we first update the velocity. We use the acceleration at point 0 to figure out the new velocity. And again, we've got to do this for several different times. I'm going to use the fact that the position is positive. That means the acceleration is negative. It's going to slope down. And that's going to give me my new velocity. Remember, this slope is based on the acceleration at the previous position. But then what I do is I use this slope to update this point. Rather than using a velocity v0, I use this negative velocity, that is the one which is sloping downwards. I use that to update my point. And that is based on the slope of v1. And now I iterate. I do the next step. First, I update this. It is negative, but not quite as negative. So the slope goes from being very steep to not quite as steep. And that's going to be the position v2. I use this new v2 to figure out what the slope is right here. It's negative. It's even more negative than it was. And we're down there. This is the slope v2. We figure out the position right here. Well, now the position is negative, so the acceleration is positive. That's v3. I use this velocity to figure out the next slope. This slope is still negative, but it's not quite as negative. To figure out x3. So there's the idea. The accelerations are being based on the previous point, but the velocities, the step from x2 to x3 is based on the next velocity. So that's the idea of Euler-Cromer, okay? And again, it will continue on. And one of the benefits of this method is it conserves energy over time. Okay, we had a question in the chat. Doesn't Euler-Cromer make the velocity graph less accurate because it uses the acceleration of the previous step every time? Well, Euler's method used the acceleration of the previous step every time. So Euler-Cromer is no worse than the Euler method. We're always using the acceleration at the previous time. So Euler is no worse than velocity. What it's doing is it's using the acceleration at the previous time, but the velocity at the next time. And that's the improvement. Euler-Cromer is sometimes called a modified Euler method because of a small change. And one of the changes that it does is, on average, it conserves energy. Any other questions about the difference between the Euler method and the Euler-Kromer method. And again, it really is just the difference between looking at it this way and looking at it this way. I know it might seem a bit pedantic to go through drawing these arrows, but as we're learning about these algorithms, it is helpful to take a sheet of paper, to go out and try and figure out the logic of, okay, which point did I use? How did I do this? How does this algorithm actually work? And sketch it out. Scrap paper is actually a very useful tool when you're dealing with numerical methods. Okay, there's an extension to this idea. We can take this idea that if it's a better idea to use the velocity at the end, why don't I also use the position at the end? One might assume, well, why don't I use the velocity at this location down here? And of course, the problem with that is I don't yet know what the position will be. I can't do both of these two steps simultaneously. But here's something we can do, is we can ask the question, what is the speed and the position halfway through this interval? This is called a mid-step algorithm or a half-step algorithm, and we can use the midpoint between the two to figure out what they're going to be. This is the idea of the Euler-Richardson algorithm. Okay, it's a little more complex, but the idea is we're going to use the value of the position at the midpoint and the value of the velocity at the midpoint in time to figure out the step size. One of the benefits of Euler-Richardson is it'll turn out you can take much bigger time steps. So what I'm going to do is I'm going to make much larger time steps. We still start off in the same way. I have an initial position and I have an initial velocity. And what I'm going to do is I'm going to use the method to figure out what the velocity would be in the middle of these time steps. So this is called the midpoint. Okay, so first thing to do is figure out what the acceleration is right at the beginning. Well, this is a positive number, so the acceleration is negative. Let's use that acceleration to come up with a mid value for the velocity. Take the current size of the velocity, multiply by the acceleration, but divide that by 2 and only take a half size step. So rather than jumping all the way from t to delta t, only go from here to here, go half the way. If you go half the way with that slope, you're going to get something fairly steep. Okay, this value right here, I'm going to call v mid, because it's the velocity in the midpoint between the step. I'm going to calculate what the position would be at the mid step. Because I don't know the velocities, I'm going to use the velocity at the beginning. The velocity at the beginning starts off at 0. So I'm using that initial velocity to come up with a mid value of the position. Then what I do is I calculate the force or the acceleration based on this new mid value. Can you see how this mid value for this particular problem doesn't change? So it has the same slope all the way through, right? And what I'm going to do is I'm going to use that acceleration to step forward all the way through on this guy right here. Okay, same slope all the way through. This guy here is V1. So far that may not look like we've done much, but here's the win. To update the new position, we don't use the velocity at the beginning of the slope or the one at the end of the slope. We use the one right in the middle. What's the velocity right in the middle? Well, it's not as small as it started at. It's not as big as it got to. It's halfway in between. It's a middle of the road kind of velocity. It's a velocity which is somewhere in the middle. And this slope, this negative slope, has the same slope as this value of V mid. No, sorry, well I'm drawing that wrong. Drawing that wrong, that's bad. Start from this point. I want to slope like this. There we go, that's better. Apologize, don't look at that. This slope right here, what we're getting right here is the, there we go. That's where I want it. Well, this diagram's going to start to fail on me here. Okay, I want something of that slope. Less bah and humbug. There's no erasers on this thing. Let us just redraw this picture so that I'm not confusing the world all the way through. V0, there's the midpoint, there's the steps. There's the final one. This is V1. This is a temporary value. This is the final value. This is the mid value. And what I want to do is I want to use this value of the slope, something that I'm calling V mid. I want to use that value of the slope to figure out what it is from here to here. I want to use that kind of slope all the way through. I want to go from here down to here. So this was the midpoint guess. This right here is x1. I am using the slope at the midpoint of here to figure out how to go to the next point. This is Euler Richardson. Beauties of paper. Nope, let's fold better than that. There, do some quick edits all the way through. Okay, let's do the next step in this process. To figure out how this algorithm is going to go to the next step, what we do is we use the acceleration right here. That is the acceleration based on the beginning of a time interval. Well, the acceleration right here is equal to 0. What do you mean by 0? Well, it's 0 because the force when there's no displacement is equal to 0. So we calculate the midpoint by using that acceleration, and we do it for a half step. Okay? So I'm going to call this V mid all the way through. We use the velocity right here, so it's very negative. We use that. It's going to be more negative than what it was. To figure out what the velocity is, a half step all the way through. The point being is it was shallow and it's more steep because this velocity is not as large as this velocity. That's the first two steps of the algorithm. The third step of the algorithm says, calculate the acceleration based on this thing, this new point called the midpoint. Well, it's a negative acceleration. Well, rather, it's a negative displacement. So it's a positive acceleration. So what you do is you go, okay, well, how positive should it be? Well, it's going to be a negative point. So we want to go upwards. We want to have a negative position is a positive slope. We do that to go all the way back up. This slope is based on the acceleration at the midpoint. But what we do then is we take this velocity, see this negative number right here, we use this velocity, even though it's not the one at the end or the beginning, we use this guy right here to do a step in one. Well, this step in one, it's fairly, it's the same value as it was before. So it gets you down to here. If you were to continue to do this algorithm, what you would see is the algorithm would do that. And what you'd be approximating is a cosine function and a sine function. Okay, so that's me trying to sketch out the algorithm. Let's flip back and look at it in terms of code, and hopefully that'll be a little bit clearer. Okay, what do I want to do? I want to investigate something called the Euler-Richardson algorithm. This algorithm doesn't depend upon the velocity at the beginning of the interval or the end. It computes the velocity and the acceleration at the midpoint. This algorithm, called Euler-Richardson, is really useful when the velocity is, the force is dependent on velocity, like it would be in a drag force, but it's useful for other problems as well. To use the model, what we do is we do what's called an Euler half-step to evaluate x mid and v mid at the midpoint. We calculate the force at that midpoint and use that to calculate the acceleration at the midpoint. Then we use those new values of mid at velocity and the midpoint of acceleration to do a full step with the Euler algorithm, a full Euler step. So here's how it looks in terms of code or an algorithm. Figure out the acceleration at the beginning of an interval. Do a Euler half step, that is, use the acceleration, the velocity to get you halfway through the interval. This is what Euler's method would have been, but we don't go all the way. Then figure out what the velocity, the acceleration should be at the midpoint. Now you have to use the mid value of x, the mid value of v, and also the mid value of t in the fully general case. And then use those velocities and accelerations to actually update the velocity and the position. Okay, let's code this up. Let's see if we can turn this algorithm into code. Being able to turn an algorithm, like it's written out here, into code is one of the skills we need to develop for this course. So here we go. Like before, I've just taken the same basic algorithm and replaced all the mentions of Euler with Euler-Richardson, the comment with Euler-Richardson, and the only real difference is down here. Euler method would have been v equals v times the acceleration dt and x plus x times old v dt. To make it Euler-Richardson, I calculate the acceleration with the old value position. Okay. This is the Euler half step. I do a half step. I don't do a full step with delta t. I only do a half step with delta t over 2. I use that old acceleration to come up with a middle point for velocity. I do an Euler half step to come up with a midpoint for position. And then the trick of the model, or the real essence of it, is I use the midpoint to evaluate the acceleration and use that midpoint of acceleration to update velocity and position. Okay, all this is to say, here we go. Couple things about this problem. Same time step, same size of delta t. If we run this for a very long time, you can see that it's nice and stable. And if you look along here, even if we make the error or the time steps quite large, it doesn't have any of that oscillating behavior. Now, there still is error. All numerical methods have error. They're not exact. But for the same value of delta t, we're able to do as well, or we're able to do better. For the same value of delta t, we're able to do better, which means you can get the same precision for a smaller value of delta t, or other way around, a larger value of delta t. As long as delta t, you can make bigger steps all the way through to get the same accuracy. It doesn't have any of the behavior of oscillating energy. You're able to make larger steps with an Euler-Richardson model. Okay, here's the payoff in Euler-Richardson. Even though the algorithm takes twice as long to do, you have to do twice as many operations, right? There's the block of code. I can take larger steps in time to be able to resolve it. So what we've covered in this lecture is 3 different algorithms. An Euler algorithm. I'll just review. There's an Euler algorithm. An Euler-Kromer algorithm, where all we've done is we've changed where we're evaluating v. And the Euler-Richardson algorithm, which is evaluating it at the midpoint, figuring out the velocity and the acceleration in the middle of every time step. The actual structure of the programs are still the same. What we're doing is we're trying to figure out how to update the model from an old state to a new state, from an old value of x, t, and v to a new set of v, x, and t. Whatever code you need to do that goes in here. This step is called an update of the model. And these kind of models are what we need to solve something to do with a simple harmonic motion. Okay, so that's all the content I need to go through in this lecture. So we haven't talked that long. I know as I was going through all this, you're probably going, oh boy, this is a lot of content. I don't know if I want to really sit here, listen through this, but I can pause here. We don't need to do any more of the theory today or go through any code. But we are starting to work with more complex numerical algorithms. So this is a great time to take a step back and ask questions about how this code is written, how these numerical models work, anything about this course. Are there any questions? A question from Nick. Could we change the 1/2 factor to a smaller method to even get a closer result? Yes. So this is only the beginning of a whole sequence of methods that are out there. We will talk about them. Euler method is an order 1 method. Euler-Richardson is an order 2 method. There are order 4 methods, and order 5 methods, and order 6 methods all the way along that you continue to explore. We will talk about this at a later time, but I will point out, because I've downloaded it for myself. Here we go. I said I've been hoping you've been looking at the textbook. This textbook talks about the modified Euler algorithms, and it talks about the Richardson-Euler algorithm. And then it says a derivation is given in Appendix 3. If you are so interested, where is chapter 3? Where is the end of chapter 3? Here we go. These are all algorithms for numerically integrating Newton's laws. And here are a number of different algorithms. Euler's algorithm, Euler-Kromer algorithm, somewhere along here. One of these texts there, buried in here, this stuff all in here, this half-step algorithm. This is the Euler-Richardson algorithm. And there are more. There are ones where you calculate x and v on the half steps, opposite half steps. There are ones where you do split the interval into 4 steps. And there's a whole family of algorithms called Runge-Kutta algorithms. We're going to talk about the Runge-Kutta algorithms as a more advanced thing in a later lecture. But the idea here is you're making steps all the way through. And there are even more numerical algorithms out there. This course is not going to look at every and all possible numerical algorithms. What I'm hoping you're able to do is if I give you an algorithm in this form, then you're able to turn that into code. And if I give you 2 different algorithms, you're able to compare them to figure out which one is better, and better in the sense of, for the same size of time step, which one has the lower error. Those are the kind of things. Okay, another question from Kayla. So, okay, here's Kayla's question. So is it that we use the various methods depending on the question? For example, Euler for projectile, Euler-Richardson from simple harmonic motion? Yes, there is no one perfect numerical model. There are different methods and they're used for different kinds of problems. Euler's method is good for pedagogical reasons, learning about this. And it's also used as a theoretical tool as building up other models. In practice, no one would ever use the Euler's method as it is for any real work. You would want to use something like our Euler-Richardson method, otherwise known as a midpoint method, for some kind of problems. For other kind of problems, ones that you want to ensure conserve energy, you'd want to use a family of models that are similar to Euler-Kromer. Euler-Kromer works the way it does because it conserves, I don't know if you've done the classical mechanics, but it conserves the Hamiltonian for the problem. Conserves energy. That's basically the long and the short of it is. You choose the model based partly on the numerics of the question, what kind of differential equation you're choosing. You also choose it based on which one performs better. So in practice, what you end up doing is you've got a particular physical problem you want to solve. You start by solving it with the Euler method because it's the easiest one to implement, very straightforward. And then you say, okay, well, does Euler-Kromer work better? Does Euler-Richardson work better? Does another model that I look up in the literature work better? And you compare them, and you're comparing them looking at error as a function of the time step. In this course, I will not say solve this problem and leave you on your own to discover which algorithm to use. Questions would always be phrased in the sense of use the Euler-Richardson algorithm to solve the following physical differential equation. Or compare the behavior of Euler to Euler-Kromer to solve this problem. And when I'm talking about comparing, it's always looking about the error in these models, or how the error depends upon the time step all the way through. Any other questions? And I said you're more than welcome to say it out loud if that would work better. Anything from assignment 2 that deserves discussion? Okay, not hearing anything. Anything about lab 2, which some of you have already done? Obviously, we're going to dive into the lab if you haven't done it before. I haven't done it yet. In lab 2, we're going to go back to, where is it? We're doing the spinning basketball problem. We're just using the Euler method for this. You could, if you wanted to, you could always change the numerical model so that you were using a different model all the way through. That's not necessary, but you could implement it that way. For those of you who have done lab 2 already, that's just fine. I will talk about one thing near the end of this lab. One of the things I want you to do is figure out, and this is the problem that we talked in the video at the end of Tuesday's lecture. We're dropping a basketball off of the Gordon Dam. We're giving it a certain amount of spin, and you see it drifting out towards the water. The question here is to estimate what value of spin you need to give it. And so what I want you to do is create a program that figures out the distance traveled as a function of this. Most likely you'll need a loop in here, something to loop through different values of omega and calculate the distance for every simulation. And again, if you haven't done the lab yet, you'll see this very soon. I've written you a piece of code that calculates how far the basketball travels. You can just use that. How do you use it? Here's an example of code that uses it all the way through. Kyle, just because you're able to look around the room, are there any questions or people like, no, we got this? Oh, your mic's off. Your mic is still off.
Dr. Munroe?
Oh, I hear a voice.
Yeah, that's Kayla.
Hi, Kayla.
I had a question about the loop because I wasn't sure how to approach it. I'm not sure if I completely understood from the lecture.
A question about the lab.
Yes, about the lab.
Okay, so how about we dive into that very soon? We'll just get you to share your screen and we'll talk about that. But is there, I think I'll stop the recording for today. Those of you who have already done lab number 2, you're done, you're free. Go and work on assignment number 2. If you haven't done lab number 2, stick around and work on that for the next hour and a bit, and we'll see you next week.